So in this presentation, we will show the actual equations for regularized linear regression, which are necessary for implementing the actual regularized algorithm. All right, so we said that regularization means that we add a penalty term to our regular cost function. So here's our regular cost function. Notice that this is the same. You're showing the fit between your model and your data, and you're taking the average overall data points. And then here you're adding this other term. And notice the 2m denominator is common to both. And that's just mathematical convenience so that you can combine them two into one expression. Okay, having this expression, we can simply apply gradient descent to minimize this function. So we can look at the equations for making that work. So we still want to update our parameters theta j by moving downhill. And then this is the parameter that controls how far you move in the downhill direction. Right? So this is nothing new, the same as before. The only thing that's changed is the expression for the derivative has changed because the function here has changed. There's an extra term. So there's going to be an extra term in the derivative. Right? So previously we found the derivative of this part, which is here. And then to find the derivative with respect to theta j of this part is quite easy because it's just theta j squared. You're going to get 2 theta j. Okay, and you have the constants theta, lambda, and 1 over 2m. So you add this term to your previous term to get the update. Now there's no change to the equation for theta 0 because, as we mentioned before, we do not regularize the theta 0 term. Now this reiterates the same point. No change for theta 0. The other terms all have just one added term. Now we can rearrange this equation to move this term together with the beginning term. And we see what happens in this regularized linear regression. Instead of taking our new theta j as theta j plus an adjustment, we're taking theta j and slightly reducing it, and then adding the same adjustment that we added before. So this tends to reduce the value of theta j relative to the previous non-regularized linear regression with lambda equal to 0. All right, looking at this term here, the alpha is typically small because you don't want your steps to be too large. So this second term here is not going to be bigger than 1. It's a reduction in theta j, not a change of sign. So typically this correction term is between 0 and 1 and a small value like 0.01. So in this case, the coefficient of theta j is something like 0.99. So you're basically shrinking your parameter before the update, which tends to have a reducing effect. Now there's a balance. It's not going to shrink down to 0. It's just a shrink compared to before. This gradient will balance some of that shrinking. Now here's a simple example where the numbers are worked out in detail. In this case, there's only 2 data rows. So the sum is from 1 to 2. So the calculations are manageable by hand. Suppose that your initial theta takes these 3 values. First one is theta 0, theta 1, theta 2. You have alpha equals 0.2 and lambda equals 1.2. These are just arbitrary choices. We'll see how to make more intelligent choices for alpha and lambda later, right? So if we calculate these updates, the theta 0 update is the same, so it's not shown. Theta 1 update, well, if you look at the update for the lambda over m times theta, first we have the theta j term. So we're looking at theta 1. Theta 1 is minus 0.1, so we have minus 0.1. Then let's calculate this term here next, the lambda over m times theta j. And that's going to multiply alpha. So here we have alpha 0.02 times lambda 1.2. And then we're dividing by 2 because m is 2 in this case. And we're multiplying by minus 0.1. So that takes care of the box in red here. And then we have the blue term. The blue term, so this shows it a little bit clearer. The box in red corresponds to this box in red here. The blue term, you have alpha over m, so that's here. And this is a sum from I equals 1 to m, so there's going to be 2 terms. You see the 2 terms here. And each term involves theta t, theta transpose times x. Now this is an inner product of vectors of length 3. So this is going to have 3 terms, which you have here, 1, 2, 3. And then you're subtracting the y. And you multiply by x. So you can follow this through in more detail. The blue here corresponds to the blue up here. Now theta 2 is not worked out completely, but it starts out the same way. Here you have your previous value of theta 2, which is 0.3. Then you have your penalty term, alpha lambda over m times theta j. Alpha 0.2, lambda 1.2, m is 2, then multiplied by the value of theta j. And then here we're going to have all the terms from the blue box. We won't show the calculation here, but it will be similar to this calculation here. You're still going to have the alpha over m. You're going to have 3 terms from the inner product, subtracting the y, and then multiplying by the value of x. In this case, it would be x2. So the remaining term here would look like this blue expression here. Now, you don't actually need to calculate the cost function when you're doing gradient descent. But if you did compute the cost function, this is how you would do it. You'd have the blue term and the green term. Blue term is just as before. Green term is quite simple. Lambda over 2m times the sum of squares. You can see the green term here corresponds to this term here. Now we've showed what's actually going on in regularized linear regression. But in practice, you would not implement the equations directly. You'd simply use a package. For instance, sklearn has this package called ridge. Another name for regularized regression is ridge regression. So here we have model equals ridge of alpha. So this sets a model with ridge regression with this parameter alpha. Now be careful about alpha. If you look at the documentation, the ridge function is minimizing this objective function. Now, notice that here we have an alpha instead of a lambda. So the alpha in sklearn's ridge regression corresponds to the lambda that we've been using in our notation. No, this function doesn't have a 1 over 2m. It doesn't matter if you take this function and divide by 1 over 2m, it's going to have the same minimum. So the bottom line is this alpha corresponds to the lambda that we've been talking about. When alpha is large, then the regularization effect is large. When alpha is small or 0, then you have unregularized linear regression. Now what model.fit does is it trains the model using features from X and outputs from Y. Then if you wanted to apply the model to other data, you'd use model.predict. And then you'd apply that to another matrix of feature data. Right, so this makes the same point that when alpha equals 10, that's actually lambda equals. Right now, we also solved linear regression using normal equations, which is a closed form solution for the parameters. It turns out that there's a closed form solution also for the parameters with regularized linear regression. You just take your x transpose x and add lambda times this matrix. Now notice the 0 here because there's no adjustment to theta 0. But these are all 1, so this adds a lambda to each of the other diagonal entries of this matrix. Now, you may know that the more strongly diagonal a matrix is, typically the more well-behaved this is. So you're regularizing the matrix by increasing the entries on the diagonal. So we had some example here of feature data and price. You'd have a 5 by 5 regularization matrix because you have 5 features. Here it's saying n plus 1 because it's taking n as the number of non-constant features, and the 1 adds another column here, so it's going to add another dimension to this matrix. All right, so that's good for regularized linear regression. We'll talk about regularized logistic regression in the next presentation.